I hope you all a very nice lunch. And now we begin our session 2. Now, may I request Professor Shobana Sharma to chair this session, and there will be 3 talks in this. Professor Shobana Sharma, please.
Hello, everyone. So this is going to be a largish session with 3 speakers, and I will request the speakers to keep to time. So let me first invite Professor Paritosh Pandya, who has been in TIFR from 1988. He was a researcher at the Oxford University Computing Laboratory, and this was as part of the Spirit ProCOS project. Pandya's main research interest lies in the area of formal methods, including real-time systems. He has been specially involved with research concerning duration calculus, including the DC valid model, model checking tool. His paper won a 2020 Test of Time Award. This is very prestigious. This was announced on the 27th IEEE Real-Time and Embedded Technology and Application Symposium held in 2021. And he has, of course, many other awards and positions. And currently he is with IIT Bombay. Paritosh, please.
No, yes.
In a minute.
Yeah, first like that. Oh. Thank you, Shobna, for that very generous introduction. It's indeed a pleasure to be here back amongst friends in this hallowed hall, and I've been asked by Bahia to talk about computing activity, at TIFR, spanning all of this 75 years, start from the era of valves to artificial intelligence. So I will try to do that. Now, throughout human history, we have passed through several revolutions. The last one was the Industrial Revolution, and people say we are in the middle of knowledge revolution. We are in information age, and which means knowledge activities are dominating the way the society is functioning in a very disruptive way. And digital computers and communication form the backbone, the nervous system through which these knowledge enterprises are being conducted. Okay, so I won't go through this detail, all of this, but the vision is that all gadgets, things around us, are going to get empowered with sensors. They will sense their environment. They will have a little bit of intelligence and computing power. They will make autonomous decisions. They will be connected to internet. So there will be worldwide internet of things apart from people. And these gadgets will talk to each other and cooperatively or competitively solve problems for us and, conduct our lives. So this includes wearable devices that we wear. It's already talking to the phone. It will soon start talking to your GP and your hospital. Your car will be in touch with the garage. And all the ACs in a big institute like TIFR may be networked, and they may cooperatively schedule their starting and stopping so that the peak load, is reduced. All of them don't start simultaneously. So extrapolating from this, there are all these visions of smart cities, smart health, energy. I won't go into it. Our government has set a big agenda of digital transformation of certainly governance, but also commerce, banking, everything. So in such a society, study of computer science as a discipline is a major area of technological growth and also of scientific study. And while this is happening now, TIFR got into the game very, very early. The story is that, okay, I can come to that story a little later. It's difficult to, it's a young subject, computer science, difficult to classify it neatly like physics, into light and condensed matter and nuclear physics. But broadly, if you look at computer science, you can say that work centers around study of these things. There are algorithms. These are step-by-step methods of solving problems. Then there are programming languages or computing systems, and you formulate your algorithm in terms of this computing system. Okay, and finally there are devices, physical devices, which follow that algorithm by executing it step by step mechanically and calculate the result for you. Okay, and then there are many applications in the artificial intelligence, cryptography, where you would want to develop algorithms specific to that area. So the subject very roughly goes like this. Now, algorithm is a step-by-step method to calculate answers to a problem, and this calculational style of working has actually been with us in science, in mathematics, in thought for ages, you know, throughout the history. For example, here is Euclid's algorithm to calculate the greatest common divisor of two integers, and it occurs in his book Elements around 300 BC. Okay, so I will not go into details of algorithm. You can all understand what it's doing. And the name algorithm comes from this Al-Khwarizmi, who was a polymath of Persian Uzbek origin. You know, he wrote some treatise on mathematics, and this became very popular in communicating Hindu, Arabic mathematics to Europe. So his two most famous books are Kitab al-Hisab al-Hindi, which is book of Indian computation. All arithmetic in India was done in a computational style. And in fact, the algorithmic style of mathematics, astronomy was very central to Indian enterprise. And I won't go into the details, but I had a few slides, but we don't have time. So Brahmagupta talks about, you know, solving quadratics. He says somebody who can do it will be called Gana, you know, a computer. And you know, Panini had this grammar system. You know, you could understand language only by parsing it into a grammatical structure. And his he had 4,000 rules, and you know, many of those rules will apply. So which one would you use? Like many moves in chess. So there are meta rules to govern these, and there will be some confusion about these meta rules. This Indian Express news is just 2 days old, 16 December. The major solution to this meta, you know, which meta rule will govern Panini system was solved by a student at Cambridge who originates from Bombay, Raj Popat. So you see, again, rule-based reasoning. So computation is being done. We use differential calculus. Again, there are calculations there, right? And calculational style of working, you know, deriving things is something that we all know. Now, of course, this algorithm is specifies what are the steps of this calculation and what is the order in which they are to be followed. And these have to be prescribed in terms of a certain notation, a certain computational model. Also nowadays we call it programming language. And you know, the prominent programming language we all know, C, C++, Java, but there has been an evolution of this language, and this mathematical computational systems in which you could specify algorithms was something that was studied by very celebrated mathematicians and logicians over hundreds of years. So here are some very prominent systems of programming, if you like. There was this golden system of new recursive functions. So here, this GCD was an example of a recursive function. In order to calculate, oh, I'm so sorry. In order to calculate GCD of numbers in B, you would reduce the problem by some simple arithmetic operations to calculating GDC of some smaller numbers. And when the numbers became small enough, you could give the answer. So you could recursively solve the problem. Similarly, you could do same computation repetitively. And the insight of computation was that very simple steps of computation, a long sequence of such steps carried out, can carry out phenomenally complex calculations and give us a power which is, you know, tremendous. Okay. Okay, so that's all I want to say about computer abstract, this programming languages or models of computation. I use models of computation rather than computational system for another reason. You know, it's not just notation. You just don't learn, you know, what are the permitted statements. You also have to understand how they behave. You know, while each statement of the programming language may be utterly trivial and simple to understand, their organization into a big program gives rise to a complexity which is very difficult to master. You know, programs are amongst the most complex artifacts made by humankind. Your Microsoft Word, you know, editor, text editor, has over 1.3 million lines of code. Your Windows operating system has over 63 million lines of code. This is not the number of parts in Apollo 11. And we've got to somehow program this thing, organize that program, understand it. So we need mathematical abstractions, to understand how programs behave. And since these programs are cast in terms of models of computation, we need to know the properties of this model. Roughly speaking, if you are building an amplifier circuit, first you have to know how the circuit elements behave. They are active or passive. You have to develop a mathematical theory of that. And then we have to have techniques by which assemblies of such components are analyzed. Same thing have to be done for programs. Okay, that's why programming languages implement certain semantics and analysis, which can be called as models of computation. Okay, so programs are written as algorithms. They are expressed in programming languages, and then we construct machines which will mechanically execute those programs. You don't have to do it by pen and paper yourself. And search for mathematical systems of programming has been over the years, by people like Goodwin or Church or Alan Turing. Studying of computing machines also goes back, far away. There are much older machines, but here is a machine constructed by Leibniz, who gave us differential and integral calculus. It was called step reckoner, which could do these 4 operations, and it was working in decimal number system. Gear positions represented what digit it was. There was a bank of gears, and somehow it could do all this. Okay, Babbage built a stored program. So after that, many fixed program computers were made. A computer, which would calculate insurance premiums because he was employed with actuaries. And for shipping, insurance you have to be calculated. He designed a specific computer for that. But Babbage went on and designed the idea of a stored program computer, a general purpose computer to which you could give previous data and give it also data when that program is to appear. So both these are fed as input to the machine, and then the machine will execute that algorithm. So now algorithm becomes input to the computer. And that revolutionary idea came first with this Babbage's machine. Babbage actually designed this machine. It was far ahead of its time to implement. We didn't have the machining technology to produce such a machine, but a model of this you can find in British Science Museum. Okay. Pardon? 18 something. I don't have. Yeah, it was quite a way back. And Shannon, all these machines work on decimal number systems with gears and rackets and pinions, transferring the state from one gear to another, etc. They are highly unreliable, very difficult to fabricate. That one, Shannon, who was the information theorist, was used to the idea of a system which could be in a number of configurations, and so each configuration carries a certain amount of information, certain bits of information. And so he naturally thought all calculation which was of interest could be cast in terms of calculations over bits. You could use Boolean algebra to do all forms of scientific calculation and communication, right? And so he propagated use of Boolean logics, and we thought digital circuits could be used to do computation. And you could put all the standard computation in decimal into this. So somebody has called this Shannon, this was his master's thesis. Somebody has called this the most impactful, most celebrated master's thesis ever. Because this revolutionized the world. This idea caught on, and people started designing digital computers from that point of it. Also, electronics was growing, which was giving us digital devices which could be used in switching modes, valves, transistors, they don't have to necessarily be in the linear part, they could be put in switching mode, right? So, and then they have to switch very fast and very reliably. So this was a happening technology, and all computers after that were designed using digital technology. Okay. Many different architectures, many different shapes of computers were tried, but the one that was called von Neumann architecture. And all the early computers, were based on von Neumann architectures. It has some limitations. We are trying to get away from it, but still, the basic background of computers that we have today is also largely von Neumann. So this has been a revolution, very, very strong idea. And what is the purpose of such a von Neumann architecture machine? Well, this idea of, machine program as a sequence of instructions, and each instruction was a simple step of calculation. Add numbers A and B, which are in some memory somewhere, and store the result into some memory location C. Okay, and there will be jump instructions which would change the flow of control. You could execute parts of code again and again repetitively. You could do many such things. So that was this thing. And the key idea was that the programming data resided in the memory. So memory had both program as well as data. And when the computer will fetch one instruction of the program at a time from the memory into the CPU, it will decode what this instruction is supposed to do. Then we will fetch the outputs of the instruction from the memory, pass on this data to P and set it up in a mode that will do the required operation, addition, multiplication, whatever the instruction said, and it will write back the result, right? And this step would be repeated again and again. We know this. This following architecture was what was followed in all of these early computers, early digital. They were all made out of valves. And question of how to build large memories was a big technological challenge that days. It was in this scene that TIFR started making digital computers. I've read it somewhere, don't hold me to it, but I think an article by Dinesh Singh or somebody which said that Nehru in one of his visits, I want to go by honorifics, excuse me for that. And one of his visits learned that computing was a strategic technology. You know, it had already broken code in Second World War. It had been used to optimize linear programming programs, you know, for during the World War for supply management and many scientific, and much of this work was underground. But he learned that computing was a strategic technology. And so he put his two generals, Mahalanobis as well as Baba, to the idea of designing an indigenous Indian computer. And they designed an analog computer at ISI Calcutta. So the first computer in India is an analog computer at ISI, but analog computing just didn't, you know, live on. You know, it had severe limitations. But Baba went in for the digital computing technology, and they designed this machine, which is now called TIFR. You know, the chief designer of the machine was Professor R. Narasimhan, who went on to get a Padma Shri for this and his other work. But actually, the work started around 52 in the electronics group, in the electronics instrumentation group. I think the group was headed by Fadke, and B.K. Basu was leading this digital computer design project. By 55, they had a prototype machine, which had some severe limitations, but we already experimented with the key digital technologies, and a prototype was already there. At that point, Narasimhan fixed the design to, you know, be like one of the standard von Neumann architecture machines, and in a very short time of 3 years, they produced this computer. Okay. I will not go too much into technical details, but it had some nice features. It encoded some fast arithmetic circuits. For example, when you're adding two binary numbers, you know, the carry has to return through all the bits, and they did not use that. That takes too much time. So they stored the carries somewhere, and they included the effect of carry on the next instruction. So, you know, what we call instruction pipelining is what was already happening there. And P.S. Rao calls this the Basu-Rao adder. Okay, there was an MQ bit which speeded up computation. There had a special place for carry bit which allowed you to change long integers into small bit sequences. Okay, so these are really good features. And perhaps the most important feature was that it used ferrite core memory in 3D matrix. This was absolutely state of the art. I think the matrix design and the backbone was imported from a company, and then the ferrite core memory was wound up here. Okay, so the machine had 1024 locations, words which it could store. Each word was 40 bits, and a read time was around 15 microseconds, and there was I/O. So I think, okay, another nice feature was that it ran from paper punch tape. I think Nagarajan referred to this. He ran programs written on paper tapes and also teletype, but there was CRT display. So you could actually display, you know, scientific functions on it. And that was very state of the art. Okay, the machine had 2700 vacuum tubes, 1700 germanium diodes, and it consumed 20 kilowatts of power. Okay, it could execute machine language programs. There was a system of machine instructions, and there was a programmer called Kane. It was a new device, and here is the photo of TIFR. Unfortunately, the machine is lost. I have not been able to see any design documents of the machine. There is one paper by R. Narasimhan in Journal of Indian Science Academy. I based some of the work on that, and P.V.S. Rao has given his memoirs. So, but some photographs are all that we have. No parts. Yeah. That is what I was told. Second floor range. See, this is all second information for me. This is much before my time. So, second floor range. CDC was second group, no. The others would have C. Okay, C wing or something. Oh no, B wing end. The C wing end. Okay. Anyway, we could find that out. And this is, the machine became operational in 60 and people started using it. 62, when we moved to this new campus, the Prime Minister Pandit Nehru inaugurated, named this machine as TIFR Advanced Calculator, TIFR. So this is certainly one of our major milestones from area of computing. Okay. The machine operated from 60 to 65. People had to be taught how to program devices like this, which was done, and then several cosmic ray people cite use of TIFR in their computation. Users were people from TIFR, BRC, some oil companies, naval dockyard, all this from previous article. And told them the demand was so much that they ran it on 2 shifts continuously every day. Okay. Around 65, the machine was decommissioned and it was presumably sent off to Bangalore. At least it started for Bangalore. Okay. So we decommissioned the TIFR around 64, 65. What happens to computer science? This is the phase 1 of computer science activity, according to me. PSRF says that even if the machine stopped, the spirit of TIFR lived on. And TIFR continued to design computing systems and system software for next 20 years. Okay, so on the strength of this, TIFR was designated the National Computer Center. It purchased a very advanced computer for that time, CDC 3600. So your last question mark is a 0. Yeah, and because our people were designers of computer, they immediately wanted to see what was inside, and they maintained the CDC machine locally. Okay, and it became a national resource. People from all around the country were taught how to program this machine. TIFR and many courses. And today, if you go to any major government lab or an academic institute, you'll find people who used to come to TIFR and program. Not just this, but the next machines that we bought also. Okay. PVSR designed a machine called for real-time data acquisition and control of physics experiments. It was used on bubble chamber experiment. And so all this era of spirit of TIFR, where we continued designing machines, I call as phase 2 of TIFR computing activity. Okay. There was a Bharati committee report which said digital technology and computing technology has to grow in the country. And because of that, Government of India set up Department of Electronics and an Electronics Commission. I think M.G.K. Menon became the first chairman of Electronics Commission. And under the umbrella of Department of Electronics, a large project called National Center for Software Development and Computing Technology, NCSD City, was formed. The story of computing activity is that, that of search for identity. It kept changing its identity. The work began with electronics group, then a computer group was formed when it became a national center, and now we have NCSD City, okay, which is its third incarnation. This was funded by Department of Electronics and United Nations Development Program, and it acquired state-of-the-art commercial computers, like 1077 or later watts, and these were used as national resources. So as I said, people from around the country came and learned how to use these machines here because it's new. Very few places had them, and then used it for their computation. And you will find this having certainly a large impact on the national computing scene. There were a few research projects carried out at NCSD City along with this facility that we had. There was a project called CCN, where they designed a computer which is a closely coupled network of multiple processors. Today we are used to having multi-core processors, right? But right at that time, they were talking about how work could be divided within multiple processors and how a machine with multiple processors could run. And so they designed this multiprocessor computer called CCN. Major challenge in systems that was the system software. The language in which operating system is to be written, the language in which you prefer. For example, to write the Unix operating system, then it was designed language C, and now we use it all. But it was designed to write the operating system. At that time, perhaps a major course in operating system design, Pergring and Son had come up with a language called Conquer and Pascal. And TIFR designed its own version called CC and Pascal. They wrote compiler for it. They wrote the multiprocessor operating system in CC and Pascal. And this design was very systematic, celebrated that a book on this multiprocessor operating system was published in the Prentice Hall CR core series, with Mathai Joseph, V.R. Prasad, Natarajan as authors. Okay, so another milestone, okay. At this time, computers started getting connected to each other and they started talking to each other. Digital communication was coming into play. Most of the communication in the country was analog. Signals were sent, at different frequencies. But digital communication was coming in. And Raman started experimenting with digital communication over satellite channels. I have a personal account. I was a young undergraduate student doing summer internship at Space Application Center, ISRO in Ahmedabad. And they asked me to design a little bit of circuit of this loop, which would communicate between Ahmedabad and TIFR over a satellite channel. You got 20 minutes per week. And they told me that the other end, there is somebody called Ramani in some place called TIFR. And I was destined to come here. So it's a very pleasant memory. But he did this experiment. And we also communicated with digital communication over telephone wires. But the major issue in digital communication is the protocol that you use in order to transfer message from one computer to another. It will not be direct connection from source to destination. It will go from several intermediate computers and switches where message may be stored. Message may be broken into packets, and each packet will be stored and forwarded at intermediate switches. Each packet will follow a different route. The most optimal route at that time is what the packet will follow. Some packets will get lost, some packets and will have to be retransmitted, some packets will have be predecessors. So protocols had to manage all of it so that you get your files intact. And there was this prominent protocols, in research domain called UCP and TCP/IP. Now we use it all. Ramani used them all and implemented an email system and a file transfer system between remote computers. The first implementation transferred these things between TIFR, VJTI, and IIT Bombay, and later other institutes got added, and a big network of universities, was formed. It was called the ERNet, which is, we still have universities with this ERNet as the domain name. So for this effort of Ramani, he has been entered into the Internet Hall of Fame, the only Indian to make it there. And this was started at TIFR. And carried on once NCSD city moved out of TIFR. Okay, I will not go into this Palatino dot, but simultaneously with Knuth designing Metropolitan locally Mudir was designing an Indian language font system called Palatino and an Indian language text processor called DOT. Okay, at that point, very large mission node projects were taken up. There was ADGIS, which was, jointly done by ECIL, Air Force, DAE with TIFR as the central node. And PVS Rao was the principal investigator, if you can use those words. Okay. He was the head of that project. And it was Air Defense Ground Environment System. It was meant for providing early aircrafts coming into Indian airspace and for tracking these. And this project was completed. These devices were manufactured by ECIL and deployed. And our registrar, who was part of the signals wing of Air Force, tells me that he has seen these devices being used almost 10 years back at Bhuj. So the devices were used. So we worked on mission node, large, sophisticated projects for the country. Telecommunications was very important. Digital communication had to move into telephony also. And Pitke was very much working in that domain. So there was a project, very ambitious, challenging project, as Pitke calls it, called AREN. It was to set up an ad hoc digital mobile communication network. Ad hoc means new nodes will join and fall out, like in a battlefield, depending on requirement. And some you had to, reliable, secure communication had to be given, and this had to go to UHF radio links, and they designed this system. The main switch was designed at TIFR. So I think Pitke gave a colloquium on this at TIFR, and some of you may remember his account of this. But carrying on from the experience of AREN, he later went on along with some Petrograd to build CDOT, the rural digital telephone exchange. Telephone exchange was, first rotary and then analog electric, and this was a state-of-the-art digital exchange of 10,000 lines only, and it had a very major effect on telephony in India. It catalyzed the use of digital telephony at affordable prices to the country. Okay, so there are these large mission mode projects. Okay, and that is phase 2 of TIFR's activity. This activity stopped around 85, but I'll go into that little later. Simultaneously with this system building and system design, very sophisticated system building and system design activity, there was, there were other things happening worldwide, See, computing machines, sophisticated as they are, is not end of the story. There is also algorithm which you want to execute on the computer, and there has to be a language in terms of which you want to express what that algorithm does, right? And there is deep sophisticated mathematics behind algorithms and models of computation because they are fairly complex objects, right? And so Dijkstra, is one of the big names in computer science and a Turing Award winner. Turing Award is our Nobel Prize, so-called Nobel Prize of Computer Science. He said computer science has as much to do with computers as telescope has to do with astronomy. Okay, and what was the other academic part, intellectual part of computer science which was being discussed? It didn't happen so much in TIFR, but also these things were going on. For example, we have to ask, how do you come up with an effective algorithm which can efficiently solve my problem? What are the strategies to be used? And nowadays we teach this in undergraduate and postgraduate programs as a subject called design and analysis of algorithms, right? For example, the GCD problem, we saw that computing GCD of a large number could be broken down to a GCD of a smaller number. This is the structure of mathematical structure of GCD computation. We can exploit this to do it. So study of this kind of things is what goes in. Okay, once you have built a program, it's a huge complex object. How do we master its complexity and understand what it does? In most branches of engineering, an artifact has a mathematical model, right? If a circuit is there, we know how circuit elements behave. If they are passive elements, we know their impedances as complex elements, and we know how when the circuit elements are connected, the assemblies behave, right? So we need a theory of semantics of the artifact that you have behaved, and you do only mathematical analysis of your artifact to find design flaws not before they are constructed. The area of formal methods addresses this question for programs and algorithms. Okay, and the question is, how are we going to model an algorithm? Can we use differential equations, linear algebra? And the answer was found in logic. Turned out that logic was very, very useful in modeling, it's a general reasoning system. It applied to this. And special logics dealing with program correctness were developed called logics of programming. These are some of the founders of it. And all 5 of them went on to win the Turing Award, our Nobel Prize, okay, for development of this. Another approach was, you treat a program as a dynamical system. It takes the current state, each statement transforms the state to another. So you have a big state space and movement between them, right? And you explore this state space algorithmically using large graph search algorithms. This approach is called model checking, and that is also become very prominent. And these 3 people, Emerson, Clark, and Sifakis, won their Turing Award for introducing this work. Now, who visited TIFR in 77? Nearly visited several times in 90s. Lamport visited 5 years back. My last dinner in TIFR Alumni was with Sifakis. So, TIFR was there. It was listening to all these ideas. And something of that carried over. I will not go over it. There are more questions to be, answered about programming, models of computation and programming languages. Maybe I will point out one, the complexity. Here we see in theory of computation given by Turing and Gödel, we need this problem can be solved by the computer or not, whether it was computable. We never worried about resources required. It was just feasibility, yes or no. Okay, in complexity theory, we started worrying about how much time an algorithm takes to produce the answer. And then we asked a much more difficult question. What is the inherent hardness of a problem? I mean, today I have an algorithm which is taking so much time, n square time, if the input is of size n, can I do an order n algorithm to solve it? These are the kind of questions that complexity theory would ask. And then it would classify problems by their hardness into groups and study interrelationships between problems. So this has been a very rich area of intellectual study in algorithms called complexity theory. Okay, I will skip this, although he is our hero. Our Nobel Prize is named, it's not Nobel Prize, our so-called Nobel Prize is named after him. But along with system building activity, through NCSDCT, a lot of intellectual training happened in TIFR. You know, UNDP and NCSDCT had resources to call international experts to come to TIFR and talk about their work. In fact, some of them are in the review board of this project. Okay, and this is a full list. Don't worry about all of it. The ones in blue are the ones who went on to win the Turing Award. Okay, so they were all here during that NCSDCT period. Okay, and they came and gave lectures, short courses, and notes. Some of these were scribed. You know, I can recall two of them. There is C.R. Ho came in 77, and there are these notes of his called Communicating Sequential Processes at TIFR, and these are before the publication of his very major paper, also called Communicating Sequential Process in Communications of ACM in 78. So we got this before the publication of the paper. Similarly, David Griscave and taught compiler construction. Keshav Nori was the main person who worked on this. Later he moved to Kanpur. I was lucky enough to learn compiler technology from Nori at Kanpur. He spread it elsewhere. Okay, another thing that happened during NCSDCT was they started an international conference which would always be held in India. Okay, and the first conference happened in 81. TIFR hosted first 6 conferences, but not in Bombay, in Bangalore for cost reasons or whatever, logistics. Okay, and this is the proceedings, you know, the cover of the proceedings of the very first conference in 81. You know, it invited, you know, who of theoretical computer science has come as invited speakers in these conferences. In fact, nowadays they all come without us having to pay for their, 10 minutes. Yeah, okay, I'll just close. Okay, and the point is, FSTTCS is in its 42nd year. It's going on right now as I speak, and most of my colleagues, instead of listening to me, are in Chennai attending the 42nd FSTTCS. It has established itself as perhaps the foremost theoretical computer science conference in Asia. Okay, and what was most important in those days is not so much interaction between international science and Indian scientists. And FSTTCS and visit of these scientists became the main conduit for absorbing trends and knowledge about academic computer science, and a generation of PhD students, including me and 4 of my batchmates, we were 5 of us, all found our PhD problems through these visitors and through these courses. So another major milestone for TIFR. Okay, some of the research directions that these visitors passed on also stuck on. One was this area of formal method, how to mathematically model a program and how to analyze it for correctness. This was led by Mathai Joseph and R.K. Shamsundar. Government would recognize that artificial intelligence was a very important problem. This is late 80s. Okay, and they funded a large project called KBCS, Knowledge-Based Computer Systems. It was a national project with 5 nodes, and 2 of those nodes were in TIFR. One was with Ramni, one was with PVS Rao. And Ramni was natural language processing and expert systems. You know, much of it become, you know, the big buzzword and the big pro. We entered this, you know, way ahead. And PVS Rao. So now in natural language processing, we don't do Google technologies on language, but these people had started working very early on it. And PVS Rao's group started working on speech technology, converting speech into written text, which is called speech analysis, and converting written text into spoken speech, which is called speech synthesis. And you know, some nice work came out through both of these. I have only 10 minutes. Finally, there was some work on real-time computations, and I will not go into this, but there was this equation that we contributed. That equation, this is for checking whether real-time programs controllers sitting on onboard computers of a space launch vehicle or a Mars pathfinder, meets all its timing requirements. And analysis of that was a problem. So this equation was solved that from TIFR. This was a slight break with the tradition, and that took root, and it's been extended in many ways. The Mars lander, I think sent in 71, actually failed because of scheduling problems. Okay, and it suffered from a problem called priority inversion. So this group from CMU actually analyzed the problem, and they said this equation could be extended with this extra term, which would take into account the priority inversion and actually solve that Mars lander inversion problem. And later Mars missions all did this calculation before sending the mission. So, this had direct influence. So this test of time award that Shobna mentioned, actually this CMU group is specifically sort of fitted for doing that analysis on Pathfinder, and the original equation is also given this award in its inaugural year in 36 years after the work. Okay. This is a table from NAC about the highlights of the period that I talked about so far. What happened was in 85, NCSD city went out. This is the end of the mission mode project work for the nations that we used to do, at least in the area of computers and electronics. Okay. NCSD city went out, Summit went out, which was a microwave research center, and TIFR abandoned technological work in electronics and computer science. That should also be called a milestone. Change of direction. India, like most nations, withdrew from designing and manufacturing own computers. The know-how was with companies, we could buy them, and the focus moved to software development and applications. And TIFR turned to the foundational scientific analysis of these objects. Okay, so we made a new beginning. In 88, a new group called Theoretical Computer Science was started. NCSD city was gone. And it had activities in two areas: formal methods, the mathematical analysis of software, and computational geometry algorithms, geometric problems, how they can be solved by computer. And Shamsundar and Subir Ghosh and myself were the three faculty members in 88. Since then, the group has grown. Currently, it has 18 faculty members in diverse theoretical areas of computer science. So, we have come far from there. Here was again a slide which was presented to NAC in 15, showing how new areas got inducted into computer science activity. In 88, this theoretical computer science group, now we are no longer NCSD city. In between NCSD city and the founding this group, Mathai Joseph was there for a year, and he started calling us FOP, Foundation of Programming. So you see, we always had this identity issue. Okay, so we are now TCS. And, work was mostly at that point in geometric and formal method. In 91, Jayakumar Radhakrishnan joined us, bringing work on algorithms and complexity theory. Okay, later several people like Kavita and Umang Bhaskar joined. Kavita has some very celebrated algorithms on what are called matching problems. If students, have preferences for which IIT they want to join, which program, which IIT, and IIT has some policies about what students they would prefer over others. How do you match students to this? This is called the matching problem. And Gale and Shepley proposed this and proposed an algorithm and got a Nobel Prize for this. This problem has become an area. There are whole conferences and courses on this, and Kavita owns some of the major algorithms in this. Similarly, works on option systems and mechanism designs. Okay, so we are working algorithm in complexity theory is one of the largest groups in TIFR. Jayakumar himself is there. He works in randomized and approximation algorithms. Okay, randomization is an interesting idea. Computer programs are definite. They do fixed things. They are supposed to do fixed things. But can you add randomness to the program, and will that give you added power to solve the problem with very high probability in short time? So if you are not guaranteed over the time, it depends on the randomness, but you are using randomness and shaping it in such a way that you produce answer A with a high probability. And then you can repeat this so that you can enhance the probability of correct solution. They are called randomized algorithms. You want to produce not the exact optimal solution, but a suboptimal. So such things are being studied. Okay. Sorry, I'll wind up now. Okay. Burkhardt came in 99, bringing the idea of system science from electrical engineering. This is control theory and also systems theory. As studied in electrical engineering. Okay, and we, instead of being a pure computer science department, we became an ECS department, like that of Berkeley or that of Weizmann. Okay, and this is the modern trend. So there are not sharp boundaries between some areas of electrical engineering and computer science. So we have a fairly modern outlook there. We became an independent school. Shobna referred to this. In 2000, Sandeep Juneja joined us, bringing in work on applied probability and queuing theory, and he analyzed, financial mathematics, banking, whole banking systems for the risk, the amount of risk they are taking, how to optimize it. And this is very sophisticated analysis using probabilities and queuing theory. So he brought that here, and nowadays he uses this for machine learning. Okay, we are Prabhakaran and Pranav Sen joined a bit later, and they started studying communication. This was the area started by Shannon, then algorithms moved into communications, protocols moved into communication, and Vinod specializes in analyzing security from the point of view of communication. How much information is there which can be leaked? So he works in information theoretic security. Okay, Pranav works on quantum information theory. Okay, and so that is the work later, and our latest addition is in the area of data science and artificial intelligence, where we are concentrating not so much on applied artificial intelligence, building one more AI system which will have, you give it a lot of data and it learns something, but the theoretical basis of how it learns. Are certain problems learnable? Okay, and we have Hari Narayanan and Piyush Srivastav Asrani joining us. So that is the current group. These are the areas. I already said that. These are the broad areas of work. And one minute can I take? Okay, so I would like to point this out. There are different sides to mathematics, and some very, very foundational areas of mathematics are studied on the 3rd floor of TIFR. In Bangalore, we specialize in differential equations, ergodic theory, things like that. But there is a bunch of mathematics which is applicable to newer computer-like systems. Okay, and this involves use of logics and automata, use of combinatorics, optimization and constraint solving, probability theory, control theory and dynamical system theory, communication theory, information theory and security game theory, data science, all the mathematics behind it. And in some sense, STCS, the computer group, has become a repository of expertise on these mathematical areas within the TIFR system. And I think that is valuable. Problems will come and change, but this will live on. Okay, so this is my final slide. Currently we have a small but world-class group. World-class group is actually words picked up from the last review of the group conducted in 2018 by very celebrated scientists, I must say. And it's focused on specific areas of computers and system sciences. It's a growing group. From 3 we became 18, and in last few years we have increased. And with the group, the average age has come down. We are well below 40 on average at the moment. At least in the last few years, there have been 7 best paper awards in some of the most prominent conferences and journals in computer science, and several of these have been won by PhD students. So that's very hard thing. And looking at the shape of things, I can only say that, the way things are going, I can expect good things to come out of here if we just go on. So thank you. That is all I have to say. Sorry.
So once more there was an effort by some young cars in the late 80s, led by Rajesh body covered to bring the DRS to the connecting organ. For some reason, PSP didn't take that, so we have